In this video, we will discuss limits. Consider the function g defined by g of t equals 4 times t squared minus 4 divided by t minus 2. Suppose we want to know the value that g approaches as t approaches 2. Clearly, we can't simply plug 2 in for t, since when t equals 2, t minus 2 equals 0, so we'd be dividing by 0. Since we test the instead, we test the value of the function as t gets closer and closer to 2, as seen in this table. When t is 1.5, g of t is 14. When t is 1.9, g of t is 15.6. When t is 1.99, g of t is 15.96, and so on until when t is 1.9999, g of t is 15.9996. We can see pretty clearly that the closer t gets to 2, the closer g of t gets to 16. In other words, as t approaches 2 from either side of 2, g of t approaches 16, or the limit of g of t as t approaches 2 is 16, written like this. The function f has a limit L as x approaches a, written lim sub x right arrow a of f of x equals L, or the limit as x approaches a of f of x equals L, if the value of f of x can be made as close to the number L as we please by taking x sufficiently close to but not equal to a. One way to determine the limit is to graph the function and see what happens as x approaches some value a from either side. If we graph the function g of x equals 4 times x squared minus 4 divided by x minus 2, we get a graph that looks like this. If we follow along the graph of g of x as it approaches x equals 2 from either side, clearly the graph crosses the line y equals 16. So the limit as x approaches 2 of g of x equals 16. However, if we were able to zoom in very tightly on that point where the lines intersect, we would see that g of x does not exist when x equals 2. There's a tiny hole in the graph because the function is undefined at x equals 2. There are 4 cases to consider when we look at limits. In the first case, the limit as x approaches a of f of x equals f of a. That is, the limit of f of x as x approaches a is equal to f of a. For example, if we look at the graph of f of x equals x cubed as x approaches 2, we see that the limit as x approaches 2 of f of x is equal to 8, and f of 2 is equal to 8. This is because f of x is a continuous function at 2. It can be drawn without lifting your pencil from the page. In the second case, there is a limit as x approaches a, but f of a does not exist. We can define a function g of x equals x plus 2 if x does not equal 1. Here, the limit as x approaches 1 of g of x equals 3. Since except at x equals 1, the function is defined by the line y equals x plus 2, which is equal to 3 when x equals 1. However, g of 1 is not defined in the definition of the function, so the function does not exist when x equals 1. In the third case, we have a function that is defined at some value a, but there is no limit. For example, in the piecewise function, f of x equals -1 if x is less than 0, and 1 if x is greater than or equal to 0, clearly f of 0 equals 0. But the limit does not exist because f of x approaches different numbers as x approaches 0 from above or below. If the limit is different from either direction, there is no limit. In the fourth case, the function is not defined at a and there is no limit. Consider the function g of x equals 1 over x squared. We can see that this function continues going upward forever, never reaching a peak as x approaches 0. Since infinity is not a number, it cannot be a limit or a value of the function. Of course, this function is dividing by 0 as x approaches 0, so we expect it to be undefined. Theorem 1, properties of limits. Suppose the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals m. R is a positive constant and c is a real number. Then, the limit as x approaches a of f of x to the r power equals the limit as x approaches a of f of x all to the r power equals L to the r. the limit as x approaches a of c times f of x equals c times the limit as x approaches a of f of x equals c times L. The limit as x approaches a of f of x plus or minus g of x equals the limit as x approaches a times of f of x plus or minus the limit as x approaches a of g of x, which equals L plus m. The limit as x approaches a of f of x times g of x equals the limit as x approaches a of f of x times the limit as x approaches a of g of x equals L times m. And the limit as x approaches a of f of x divided by g of x equals the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, which equals L divided by m, provided m does not equal 0. Evaluate the following limits. The limit as x approaches 2 of x cubed is equal to the limit as x approaches 2 of x quantity cubed, which is equal to 2 cubed, which is 8. The limit as x approaches 4 of 5x to the 3 halves equals 5 times the limit as x approaches 4 of x, all raised to the 3 halves, which is 5 times 4 to the 3 halves, which is 5 times 8, which is 40. The limit as x approaches 1 of 5x to the 4th minus 2 equals the limit as x approaches 1 of 5x to the 4th minus the limit as x approaches 1 of 2, which is 5 times 1 to the 4th minus 2, which is 5 times 1 minus 2, which is 5 minus 2, which is 3. The limit as x approaches 3 of 2x cubed times the square root of x squared plus 7 equals the limit as x approaches 3 of 2x cubed minus the limit as x approaches 3 of x squared plus 7 equals 2 times 3 cubed times the square root of 3 squared plus 7, which is 2 times 27 times the square root of 9 plus 7, which is 54 times the square root of 16, which is 54 times 4, which is 216. The limit as x approaches 2 of 2x squared plus 1 divided by x plus 1 is equal to the limit as x approaches 2 of 2x squared plus 1 divided by the limit as x approaches 2 of x plus 1, which is 2 times 2 plus 1 divided by 2 plus 1, which is 8 plus 1 divided by 3, which is 9 divided by 3, which is 3. A function is said to have an indeterminate form if, when a limit is taken as x approaches some value, the function results in a meaningless expression such as 0 divided by 0. For example, the limit as x approaches 2 of 4 times x squared minus 4 divided by x minus 2 becomes 0 divided by 0 if we evaluate the numerator and denominator when x equals 2. To evaluate indeterminate forms, replace the given function with an appropriate one that takes on the same values as the original one everywhere except at x equals a, and then evaluate the limit of this function as x approaches a. For example, we can evaluate the limit as x approaches 2 of 4 times x squared minus 4 divided by x minus 2 by noticing that x squared minus 4 is equal to x plus 2 times x minus 2. So we can change the function to 4 times x plus 2 times x minus 2 divided by x minus 2, and then cancel the x minus 2 in the numerator and denominator. We're left with 4 times x plus 2 equals 4x plus 8. Now we can easily take the limit as x approaches 2 of 4x plus 8 equals 4 times 2 plus 8 equals 8 plus 8, which is 16. Or we can evaluate the limit as h approaches 0 of the square root of 1 plus h minus 1 over h. If we let h equal 0 and evaluate, we get 0 divided by 0. No help. So one thing we can do to change this function is multiply numerator and denominator by the conjugate of the numerator, the square root of 1 plus h plus 1. So the limit as h approaches 0 of the square root of 1 plus h minus 1 over h times the square root of 1 plus h plus square root of 1 plus h plus 1 divided by the square root of 1 plus h plus 1 is equal to the limit as h approaches 0 of 1 plus h minus 1 over h times the square root of 1 plus h plus 1, which is equal to the limit as h approaches 0 of h over h times the square root of 1 plus h plus 1, which is equal to the limit as h approaches 0 of 1 over the square root of 1 plus h plus 1, which is 1 over the square root of 1 plus 0 plus 1, which is 1 over the square root of 1 plus 1, which is 1 over 1 plus 1, which is 1/2. Sometimes we want to know if a function approaches a specific number as the independent variable increases or decreases without bound. Given the function f of x equals 2x squared over 1 plus x squared, if we want to determine what happens to f(x) as x gets larger and larger, we can pick a sequence of increasing values and calculate the corresponding values of f of x. If x is 1, then f of x is 1. If x is 2, then f of x is 1.6. If x is 10, then f of x is 1.98. If x is 1,000, then f of x is 1.9999998. We see that as x gets larger and larger, f of x gets closer to 2. The graph of the function confirms this observation. We call the line y equals 2 a horizontal asymptote. We say that the limit of the function f of x as x increases without bound is 2. Written, the limit as x approaches infinity of 2x squared divided by 1 plus x squared equals 2. The function of f has the limit L as x increases without bound, or as x approaches infinity. Written, the limit as x approaches infinity of f of x equals L, if f of x can be made arbitrarily close to L by taking x large enough. Similarly, the function has the limit m as x decreases without bound, or as x approaches negative infinity. Written, the limit as x approaches negative infinity of f of x equals m, if f of x can be made arbitrarily close to m by taking x to be negative and sufficiently large in absolute value. For example, let g of x equal 1 over x squared. Evaluate the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of g of x. That should be f of x again there. Sorry, the first one should be g of x, not f of x. So the easiest way to evaluate this is to look at the graph of the function. We can see that the limit as x approaches infinity of g of x equals the limit as x approaches negative infinity of g of x equals 0. All of the properties of limits listed in Theorem 1 are valid when a is replaced by infinity or negative infinity. Additionally, we have Theorem 2. For all n greater than 0, the limit as x approaches infinity of 1 over x to the n is equal to 0, and the limit as x approaches negative infinity of 1 over x to the n equals 0, provided that 1 over x to the n is defined. Most of the time, we will look at limits of rational functions, a function where the numerator and denominator are polynomials. There's a nice simple way of finding limits at infinity for these functions. First, rearrange the terms in the numerator and denominator so the term with the highest power is first in each case. Then compare the powers of the terms with the highest powers. If the highest power in the numerator is greater than the highest power in the denominator, the limit as x approaches infinity of the function is positive or negative infinity, depending on the ratio of the coefficients of the highest powers. If the highest power of the numerator is equal to the highest power of the denominator, the limit as x approaches infinity of the function is equal to the ratio of the coefficients of the highest powers. And if the highest power of the numerator is less than the highest power of the denominator, the limit as x approaches infinity of the function is 0. For example, evaluate the limits. The limit as x approaches infinity of x squared minus x plus 3 over 2x cubed plus 1. The highest power of the numerator is 2 and the highest power of the denominator is 3. The limit is 0. The limit as x approaches infinity of 3x squared plus 8x minus 4 over 2x squared plus 4x minus 5. The highest power in both numerator and denominator is 2, so the limit is the ratio of the coefficients of the highest powers, 3 over 2. The limit as x approaches infinity of 2x cubed minus 3x squared plus 1 over x squared plus 2x plus 4. The highest power in the numerator is 3. The highest power in the denominator is 2. The limit is plus or minus infinity, depending on the ratio of the coefficients. Since the ratio of the coefficients is 2, the limit is infinity. The limit as x approaches negative infinity of 2x cubed minus 3x squared plus 1 over x squared plus 2x plus 4. Since the difference in the highest powers in the numerator and denominator is odd, the sign of the limit changes going from one end to the other. The limit is negative infinity. Notably, if the difference in highest powers is even, the numerator has a higher power than the denominator. The sign of the limit stays the same.